My lab was on light reflection of different colors. These were the different colors I reflected the light on. I used a LED, which was white. Later, I used a vernier spectroscope to measure the reflected spectrum. In the first trials, I used this to measure how much light was coming off the surface. The purpose was to figure out how much light was coming off different surfaces. Later, because the first trials did not turn out the way I wanted them to, I did a bunch of research on how the human eye works and how different color wavelengths work, and I readjusted the purpose to figure out how different colors' wavelengths were compromised. This was the data for the most obvious colors. White was really high on everything, which is what I expected, and then black was really low. Next was key lime, which was like a light green. It was very high on the green. And then bluest, which was a dark blue, and it was really high on the blue. When I got this data, I started getting a little confused because I thought colors were an individual wavelength and that I could find that wavelength and then relate it to the amount of light reflected. So I had to realign my priorities to understand why there was 3 different peaks and how that resulted in a purple when there's green and red and blue in it. This is basically what I just said, that colors have multiple wavelengths in them. The eye has 3 different cones, red, green, and blue, which when combined in your brain give you the colors that you see. Okay, this is the demonstration part. Can I have like one half of the class to come up here and stare at the red?
Sure. Which half?
Yes.
Can I just sit here?
Teddy, don't trust Teddy. He's colorblind.
Yes.
Teddy, get up.
Okay, why did that greener than normal thing happen when you stared at the red? Well, this is the 3 different cones in the eye. We have the blue, green, and red. The green, which is like about here, like the greenest color that you can see, it has a lot of red in it. So after you stare at the red for a really long time, After you stare at the red for a really long time, you get less sensitive to it, and then when you swap to the green, this red that you normally see and the green isn't there, so it's greener than it normally would be to your brain. Okay, I'm good. Or done.
But that's your conclusion?
Sure. I decided to talk about one part because I could have spent like half an hour on like all the different things about the eye.
Well, maybe there are some questions.
Okay, any questions?
There are probably some questions. Just give them a moment.
Elizabeth?
What did you do again? Like, what was it?
The thing with the colors?
Yeah, like, what was it just procedure?
For like my experiments?
Yeah.
I took a light and then shined it against a background that was different colors, and then I measured the reflection off of it. Ian?
What exactly were like the question that you're trying to figure out? Was it just about the colors, or
I was trying to see how much light and what kinds of light the different colors reflected. Madeline?
The demonstration that you did, does that only work with red and green, or does it work with other colors too?
There's more overlaps, but the red and green is the most noticeable one. Daniel.
So this is related to like a red-green color blindness, correct?
Yeah, they have so much related that if you have like cone deficiency, you probably see them the same. Okay, good?
Cool. Thanks again.